Did you know that the secret to the world's tallest skyscrapers and strongest bridges isn't just about what ingredients go into the concrete, but exactly how microscopically small those cement particles are? If the cement is too coarse, your concrete will be weak and bleed water. Too fine, and it could overheat and crack before it even cures. Today we are cracking the code on cement fineness. Welcome back to the Certified MTP channel, your ultimate destination for material testing equipment, industry standards, and testing tutorials. If you want to ensure your construction materials are up to code, you are in the right place. Today we are diving deep into one of the most critical quality control measures in the cement and concrete industry, the cement Blaine air permeability apparatus test. We are going to explain exactly why fineness matters, the physics behind how we measure it, and do a complete walkthrough of the testing process. To do this right, we will be showcasing the top-tier tools for the job, specifically the Blaine apparatus, electronic and semi-automatic, and discussing why you absolutely cannot perform this test without the gold standard of calibration, the NIST 114R Portland Cement Fineness, SRM number 114R, 20 per package. Whether you are a lab technician, a civil engineering student, or a plant manager looking to upgrade your testing accuracy, this video is your comprehensive guide. Before we touch the equipment, we need to understand the why. Why do we care about the size of a particle of dust? Cement is the binder that holds concrete together. When you add water to cement, a chemical reaction called hydration occurs. This reaction is what gives concrete its strength. But here is the crucial part. Hydration only happens on the surface of the cement particle. Therefore, the smaller the particles, the greater the total surface area per gram of cement. A higher specific surface area means more of the cement is exposed to the water right away. This leads to a faster reaction, which means your concrete will gain its early strength much more rapidly. But it is a delicate balancing act. If you grind the cement too fine, it costs the manufacturing plant a fortune in energy. Worse, ultra-fine cement reacts so violently and quickly that it releases a massive amount of heat, known as the heat of hydration. In large pores like dams or massive foundations, this excess heat can cause severe thermal cracking, compromising the structural integrity of the entire build. To prevent these catastrophic failures and guarantee consistency, regulatory bodies like ASTM International establish strict testing protocols, specifically ASTM C204 and AASHTOT 153. These standards require us to measure the specific surface area of cement, expressed as square centimeters per gram, the square centimeters per gram, or square meters per kilogram, the square meters per kilogram. And how do we measure the surface area of microscopic dust? We use air. You can't take a ruler to a grain of cement. Instead, we use the principle of air permeability. The core concept is brilliantly simple. If you pack a specific amount of cement into a small, standardized bed, the spaces or voids between those particles will allow air to pass through. If the cement particles are large and coarse, the voids between them are larger, and air will flow through very easily and quickly. If the cement particles are incredibly fine, they pack tightly together, creating tiny, tortuous paths. Air will struggle to push through, taking a much longer time. By measuring exactly how long it takes for a fixed volume of air to pass through a prepared bed of cement of a known porosity, we can calculate the specific surface area. This procedure is universally known as the cement Blaine air permeability apparatus test. Historically, this was done manually with a standard U-tube manometer, a stopwatch, and a very steady eye. The technician had to manually draw the fluid up the tube using a rubber bulb, wait for the fluid to drop, and click a stopwatch the exact millisecond the meniscus passed the timing marks. It leaves a lot of room for human error. That is why today, for our demonstration, we are using the Blaine apparatus, electronic, semi-automatic. This piece of equipment is a game changer for high-volume material testing labs. By automating the timing process, it completely removes human reaction time from the equation, providing hyper-accurate, repeatable results that you can trust batch after batch. But having a high-tech machine is only half the battle. A testing apparatus is absolutely useless if it isn't properly calibrated. Air pressure, temperature, the exact viscosity of the manometer fluid, and minor variations in the apparatus itself will all skew your results. To solve this, the entire industry relies on a specific calibration standard. You cannot perform a valid Blaine test without it. I am talking about the NIST 114R Portland Cement Fineness, SRM number 114R, 20 per package. NIST stands for the National Institute of Standards and Technology. They manufacture this standard reference material, SRM. When you purchase the NIST 114R Portland Cement Fineness, SRM number 114R, 20 per pack. From certified MTP, you are receiving a pack of 20 glass vials, each containing roughly 5 grams of cement that has been measured and verified to an almost unimaginable degree of precision. The certificate that comes with this SRM tells us exactly what the specific surface area of this specific powder is. By running a test on the NIST 114R cement, we establish an apparatus constant. We tell our machine, when you test this specific powder, the answer should be X. Once the machine is calibrated to this undisputed gold standard, we can then test our unknown daily production samples with total confidence. Let's get hands-on and run through a complete cement Blaine air permeability apparatus test. We will use our Blaine apparatus, electronic, semi-automatic, to show you just how streamlined this process can be. Step 1. Determining the density. Before you begin, you must know the precise density of the cement you are testing, usually determined using a 𝐒𝐿 flask. We also need to determine the exact volume of the stainless steel permeability cell we will be using. Step 2. Preparing the sample. We take our cement sample, whether it is our calibration standard or our production mix, and we must ensure it is at room temperature. We place it in a small jar and shake it vigorously for exactly 2 minutes to fluff the cement and break up any microscopic lumps or agglomerations that form during storage. Step 3. Preparing the permeability cell. We take our permeability cell and place the perforated metal disc at the bottom. Next, using forceps so we don't transfer oils from our skin, we place a single, perfectly sized disc of standard filter paper flat on top of the metal disc. Step 4. Weighing and loading the cement. Using the density of the cement and the volume of our cell, we use a specific formula to calculate exactly how much cement is required to create a bed with a target porosity of 0.500. We use a high-precision analytical balance to weigh out the exact gram amount, down to the thousandth of a gram. We pour the cement into the cell, tapping the sides gently to level the surface. Step 5. Compacting the bed. We place a second piece of filter paper on top of the cement powder. Then we insert the specialized metal plunger. We press down firmly until the collar of the plunger comes into complete contact with the top of the cell. This compresses the cement into a perfectly uniform bed with an exact known volume and porosity. We slowly withdraw the plunger. Step 6. Running the electronic test. We carefully seat the permeability cell into the top of the manometer, ensuring an airtight seal. If there is a leak here, the test is void. Now, if we were using a manual apparatus, I would have to use a bulb to suck the air out of one side of the U-tube, drawing the fluid up past the top timing mark, close the valve, and sit with my stopwatch. But because we are using the Blaine apparatus, electronic, semi-automatic, the machine takes over. I simply press start. The internal microprocessor automatically activates a small pump, drawing the manometer fluid up to the correct height. It then shuts off the valve automatically. As the air slowly forces its way through our compacted bed of cement, the fluid level drops. Built-in photoelectric sensors detect the exact millisecond the meniscus of the fluid passes the upper mark, starting the internal timer. As it passes the lower mark, the timer stops. No human reaction time, no squinting at lines, just pure, precise data. Testing cement fineness is critical for structural safety. Don't risk it with outdated gear. Upgrading to the semi-automatic Blaine apparatus means faster testing, fewer human errors, and strict ASTM C204 compliance. And don't forget to routinely calibrate with NIST 114R standards. Ready to elevate your lab? You'll find direct links to the Blaine apparatus, calibration standards, and all necessary accessories in the description. Head to certifiedmtp.com to gear up. If this breakdown helped, hit that like button, comment any questions below, and subscribe to Certified MTP for more industry insights. See you in the next test.